Hello, scholars. It is me, Mix Peglin. First of all, I apologize for the delay in getting these videos to you, and I will try to make them as brief as possible. So, we've been learning about particles, how they interact with each other. Today, we are going to talk about how heat affects the temperature and kinetic energy of particles, and really what that means in terms of how particles transition from one phase of matter to another. Phase changes are incredibly important. They drive the water cycle, which ultimately drives our climate, so pretty exciting topic. And today we're going to dive into the calculations associated with phase changes, as well as explain, what is happening as molecules as the phase change is occurring. So let's say we start with a sample of water at negative 10 degrees Celsius, and we add heat energy to it, energy in the form of heat, at a constant rate. Hang on, sorry, scholars, I'm not as good as Professor Dave. Here we go. Heat is a type of energy. It's indicated as Q, and it is measured in joules or kilojoules. Okay? So, and this is our temperature, obviously, in degrees Celsius. We're adding heat to our water at a constant rate. And as we do that, the temperature of our sample of ice steadily increases. So if our temperature is increasing, what is happening? There we go. Haha. So our temperature is increasing. That means we know our kinetic energy is also increasing, right? Then we hit 0 degrees Celsius and something weird happens. We're still adding heat, but our temperature remains constant. So our temperature is constant. We know our kinetic energy stays the same. So what's going on at this point? Well, I've used water as an example because we know that 0 degrees Celsius is the melting or freezing point of water. Same point, measuring in different directions. Freezing point measures liquid to solid, melting point measures from solid to liquid. Okay? Point being, we're adding heat, our temperature is constant, our kinetic energy stays the same. Where is our energy going? Well, I'm going to tell you. Our energy that we're adding along this line is going to break the intermolecular forces that keep the water in the solid phase. So right now we are breaking IMFs, and we are undergoing a phase change. And in this case, it is from solid to liquid. All right. So now once all of our ice has turned to liquid water, we continue adding our heat. Our temperature continues to increase. Our kinetic energy is increasing until we hit 100 degrees Celsius. And then the same weird thing happens again, where we're still adding heat, but our temperature isn't changing. So what's happening to that energy? Well, it is breaking our intermolecular forces in the liquid stage so that we can phase change from gas to the liquid. And then, once all of our water has turned to steam, we continue heating our sample, and at this point, the kinetic energy of our sample will continue to increase because our temperature is just continuously increasing. So this is the basic format for pretty much any heating curve. You have your solid, liquid, and gas segments, and then you have your two phase change segments. Question: why is the segment for the phase change from liquid to gas so much greater than the phase change from solid to liquid? Well, I will tell you. The reason is because in the phase change from solid to liquid, we are breaking some intermolecular forces. Remember, in liquids, we still have IMFs. However, as we go from liquid to gas, gases pretty much don't display IMFs. So we're breaking all of the IMFs, which is, of course, going to require more energy. All right, so now let's move to calculations. There are two equations that we need to be familiar with in order to perform heating curve calculations. The first is Q, so heat energy is equal to mass times the specific heat capacity times delta T, which is your change in temperature. Okay? The second is Q equals, so Q is our heat energy, equals our mass times our heat of vaporization or fusion, which basically means the heat associated with a phase change. So, we're going to start with this equation. This equation is used when we are in these parts of our heating curve. When we are not changing phases, we are just heating our sample and our temperature, our kinetic energy is increasing. So, basically you can read this as the heat energy is equal to the mass of the sample times its specific heat capacity times its change in temperature. So, new concept, specific heat capacity. Is the amount of energy required to raise the temperature of 1 gram of a substance by 1, nope, all right, pretend that that's a degree sign, degree Celsius. Its units are joules per gram Celsius. Okay? And I'm going to show you how to use these equations, and we're going to get a whole bunch of practice with it in class. So then we have these equations, which are really the same equation. It just depends if you're using the heat of fusion or the heat of vaporization. And these are associated with our phase change. Okay? So now, Q equals heat energy. M is our mass of the sample. Heat, H is the heat associated with the phase change. So heat of fusion is how much heat energy you need to transition to and from solid and liquid. Okay? And our heat of vaporization is how much heat energy you need to transition, technically 1 gram. to and from our liquid and gas phase. So vaporization, you're vaporizing it, and heat of fusion, you're fusing it together. And the unit for both of these is joules per gram. Okay? So now let's move to some practice problems. This video is already longer than I wanted it to be, but that's okay. Calculate the amount of heat released when 0.93 grams of water cools from 55 degrees Celsius to 44 degrees Celsius. The specific heat of water is 4.81 joules per grams degree Celsius. So what equation are we going to use? That's right, we're going to use this equation because we're dealing with a temperature change. So we're calculating Q. We have our mass of water. Specific heat capacity of water is 0.481 joules per gram degrees Celsius. Like I said, pretend that that's a degree sign. And we calculate our change in temperature as delta T is equal to the final temperature minus the initial temperature, right? So here's our final, here's our initial. These are in Celsius, Celsius. Okay. Just an important note, this specific heat of water is very, very high. And that has some very critical implications for Earth's climate. Basically, Earth's climate could not exist as we know it if the specific heat capacity of water was not this high. This allows water to moderate Earth's temperature. Why do you think the specific heat of water is so high? I'm going to leave that as a hanging question that we will discuss in class. So, to finish up our calculation, we just plug and chug 9.03 times 4.81 times negative 11, negative 415, which I'm going to round up, negative 416 joules. Okay, and this negative sign is very important because it indicates that we are releasing heat. There is less energy in the system at the end of this situation than in the start. So the other way to say this is 416 joules released. Okay. Now we're going to go to practice problem 2. Calculate the amount of heat required to melt 11.9 grams of water. The delta heat of fusion is 333.5 joules per gram. So we're dealing with a phase change. We're dealing with melting, so this is the equation we're going to use. Q equals mH fusion. Yep. We're calculating heat. All right, our mass is 11.9 grams. Our heat of fusion is 333.5 joules per gram. Forgot my units, can't do that. And our heat is equal to 11.9 times 333.5. I'm going to do 3 sig figs, 3,000, 3.4 times 10 to the third joules, which is 3.40 kilojoules. And the reason I'm converting it to kilojoules is because it allows me to get rid of this exponent. So there you have it. That's heating curves. Those are the types of calculations you're going to be doing with heating curves. We're going to practice a lot more on Monday, so I will see you all then. Bye!